Imagine being able to soar through the entire universe in just a matter of seconds. You, as a space explorer, could hop onto any planet you wish and discover its natural beauties, go sightseeing, then maybe even get a taste of its vibrant cultures. Yet for now, these are simply fantasies, figments of our imagination that exist only within ourselves. Sadly, it'll take countless years to even travel outside of our own solar system, let alone explore the entire universe. But it's the possibility of doing so which we cling on to in hopes of making it a reality one day. For now, the only way to travel through space is by means of a rocket ship. Rockets in fact work on a set of basic physics principles which you are familiar with, and this video will build upon these simple ideas and demonstrate the application to universal flight. It's a lot easier than you think. It's just rocket science. The dynamics of launching a rocket into the air work by applying Newton's 3 laws of motion and the principles of momentum. A rocket uses an exhaust to move. The exhaust is created by releasing pressurized fluids through different means, such as through a combustion reaction. The rocket's exhaust exerts a force against the launch pad. Due to Newton's third law, the launch pad exerts an equal and opposite force onto the rocket, which is in an upward direction. A rocket begins at rest on the launch pad. In order for it to change its state of motion in accordance with Newton's first law, it has to experience a net force. Therefore, the rocket must produce a thrust force greater than the force of gravity which opposes it in order to increase its velocity and therefore accelerate. For rockets, increasing the net force is not as simple as applying Newton's second law, since they are a variable mass system. This means that unlike other objects, their mass changes over time. That's because as the rocket travels, its mass decreases by an amount equal to the mass of the exhaust fluids released. It is important to note here that momentum is conserved and the total mass of the entire system, which includes the rocket and its exhaust, is constant. So to understand this better, let's analyze a rocket in motion. Now consider from two different inertial frames of reference. The first reference frame is from that of an observer inside of the rocket. From their perspective, it appears as though the exhaust is moving backwards at some velocity. This can be defined as the velocity of the exhaust relative to the rocket, or in the diagram, VER. From the reference frame of an observer on the ground, they see the rocket moving forward and the exhaust trailing behind it. We can define the velocity of the rocket relative to the ground as VRG, and the velocity of the exhaust relative to the ground as VEG. From kinematics, we can apply the method used to add relative velocity vectors to determine the velocity of the exhaust relative to ground. Now that the vector addition operation is set up, we need to reevaluate the motion of the rocket from the reference frame of an observer on the ground. In reality, this is what occurs. Let's consider that the system begins moving in uniform motion at some velocity v, or at rest. Now, the word system is being said since the rocket and exhaust are components of it, and at the moment, they are moving together. The rocket then gains velocity, hence accelerating it forward, so this represents a change in velocity represented by delta v. This new velocity can be written as the following expression. Since this is from the reference frame of an observer on the ground, the velocity of the rocket as it accelerates can be equated to its relative velocity. We can substitute this value into the addition of relative velocity vectors from earlier on. Now, add these vectors and define the velocity of the exhaust relative to the ground using them. This motion all takes place in one dimension, so to simplify everything, define the direction to the right as positive and the direction to the left as negative. Now all vectors will be defined in terms of one direction, which will be towards the right. Therefore, the vector for the velocity of the exhaust relative to the rocket will become negative. The velocity of the exhaust relative to the ground is now equated to this. This is important to know since we are going to apply the law of conservation of momentum to this. The system has an initial momentum of the mass of the rocket defined by m, multiplied by its velocity defined by v. We'll apply what I began to discuss earlier on mathematically now. The system experiences a change in mass signified by delta m, which is a negative quantity. By looking at this entire system, its mass altogether is constant. However, it is being split amongst the system's components, which are the exhaust and the rocket. This results in the exhaust gaining a mass and the rocket losing an equal amount of mass. The rocket moves at a velocity relative to the ground, and so does the exhaust. We have already defined these quantities. Therefore, the following equation can be used to represent final momentum. this represents momentum of the exhaust, and this is the momentum of the rocket. There's a negative sign besides the expression for exhaust momentum, since these are all vector quantities. Vectors are being added, and they're all in the same direction, so algebraically they should all be positive values being summed together. Delta M, remember, is negative, so a negative sign is there to ensure everything is positive. By the law of conservation of momentum, the following equation can be created. Now, let's simplify it. This is the result we are left with. Now, to decode these letters, what you see on the left is the momentum produced by the rocket's exhaust. The negative sign means that the momentum of the exhaust is in the negative direction, which we defined as to the left. The momentum of the rocket itself is in the positive direction, to the right. Physically, the equation means that as more mass is transferred to the exhaust and it moves at a higher velocity, the rocket itself will travel at a greater momentum, which is independent of how much mass it has lost. In fact, the rocket experiences an impulse as its momentum is changing due to the properties of the exhaust. This indicates that a net force is acting upon the rocket by the exhaust, causing it to accelerate. This can be simplified further by dividing both sides by t, which represents time. Finally, the equation simplifies to this, where the net force acting upon the rocket is equal to the velocity of its exhaust relative to the rocket, multiplied by the rate of mass ejection. This is the net force acting upon the rocket, which allows it to reach a desirable velocity as it travels. To figure out the thrust force, it is necessary to take into account other forces acting upon the rocket, and then use the net force equation from Newton's second law of motion to figure out missing variables. This video went over the forces that act on a rocket as it launches, and the mathematical derivation of determining the net force acting on the rocket initially. Now that you know a bit more about the physics behind basic rocket science, let's delve into why rockets are necessary for our future. The Earth is running out of resources due to an exponentially increasing population, and so it is necessary to turn to other bodies in space to find valuable materials or a place to inhabit. With the privatization of rockets, now there is a new economy forming around space-based endeavors, which has the potential to rake in a lot of money and jobs to help the global economy. One of these great ideas is asteroid mining, which involves collecting hydrogen, carbon, nitrogen, and oxygen to use it as rocket propellant, and also in other industries that may need it on Earth. Although national space programs are very expensive, the costs lie in the ethical priorities of the corporations that work for the government, not in the production of the rockets themselves. Boeing and Lockheed Martin, who produce rockets for the U.S. National Department of Defense, do not publicize their prices. However, the Evolved Expendable Launch Vehicle, or EELV, program costed the U.S. government $1.14 billion to fund for 3 launches. That is because Boeing and Lockheed Martin hiked up their prices to earn a profit, roughly $318 million per launch. However, in reality, space travel is much less expensive, as proven by SpaceX, which has taken on the same task for a contract price of only $86 million, which is much less. Space travel is very expensive, however, it is necessary for humans to leave the Earth and discover the universe. This planet may be uninhabitable in a few hundred years, so we must do everything we can to survive, and this may require us to migrate to another planet that we could live in. As well, the money that we earn could go towards helping poverty or healthcare, but the same can be said about the wars, which are often fought for trivial reasons. So, I believe that it is much better to invest the money which we have and set our new race into an era of intergalactic exploration. Note, the purpose of this video is that it is to be used as an educational resource for students at the high school level. It is meant to inspire them to contribute to the industry as they grow older and make an impactful difference for the world. Please share this with your class if you're an educator, or if you're a student, discuss your findings with your peers. Thank you.